In this video, we're going to look at experiment 13, which focuses on colligative properties. To give you some examples of how colligative properties are relevant to the real world, examples of applications that use colligative properties are things like using road salt in the wintertime to melt ice and snow. The salt, when you add it to the ice and snow, dissolves into the ice liquid mixture, lowers the freezing point, and then causes the ice to melt. Another application is in radiators of cars. So antifreeze, which is something that you put into the radiator, you add ethylene glycol to water, and that mixture both raises the boiling point and reduces the freezing point. So in the wintertime, when your car is sitting outside, it won't freeze, causing your radiator to crack because of the formation of ice in the radiator tubing. And then also, when you turn your car on and you actually want to drive, and the car starts to produce heat, this fluid can heat up beyond the boiling point of water, allowing it to remove heat from the engine and to keep the engine cool. Your blood plasma is also a very good example of a solution, and there is a significant antifreeze quality to your blood because of all of the different solutes like proteins, salts, electrolytes, and other solids that are dissolved in your blood plasma that allow you to maintain a liquid blood plasma in your body. And then another one is de-icing agents on aircraft. So when you are flying in a plane and it's wintertime, you'll notice that they'll spray this hot liquid on the wings. Not only is the liquid hot, which will melt the ice, but it also has ethylene glycol in it, like antifreeze, and that sticks to the wings and prevents new snow that falls from freezing on top of the wings. So what we're going to focus on today is freezing point depression. And in particular, freezing point depression, the equation for it is delta T of freezing, meaning the change in temperature of the freezing point is equal to the Van Hoff factor I times Kf, which is the freezing point depression constant, times the molality. So again, all colligative properties depend on the concentration of the solvent, and the more concentrated the solvent, depend on the concentration of the solute, and the more concentrated the solute is, the larger the effect, in this case, the freezing point depression, will be. Now, because we have a freezing point depression, what's going to wind up happening is the solution temperature is going to be lower than the solvent temperature. So normally the delta T is reported as a positive number. So for that to be the case, we would have to have the temperature of the solvent minus the temperature of the solution to be the delta T. So the solvent is going to be some higher number. For water, this would be 0 degrees Celsius, and then if you were to add salt to water, the temperature of the solution would be a negative temperature in degrees Celsius, so like maybe negative 5 degrees Celsius, which would then give you a positive delta TF. So how can we use freezing point depression to determine the molecular weight? A key component of this experiment will be that we're going to use freezing point depression to measure the molecular weight of an unknown solute. Now, one thing that's important to mention at this point is this unknown solute does not ionize, so its Van Hoff factor is going to be 1. So throughout this experiment, you're going to use an I equal to 1. I just want to mention that now. I'll also mention it again when we get to the data analysis. So to get a molecular weight, we need two things. We need to have the mass of the solute, and we need to have the moles of the solute. So if we have those two things, we can get a molecular weight. Now, the other thing that we're going to do is experimentally, we're going to measure the freezing point depression of a pure liquid, and we're going to measure the freezing point of a pure liquid, and we're going to measure the freezing point of a solution, and that's going to allow us to get this delta T factor. So let's look at how we can use our freezing point depression equation to get a molecular weight. So the little m stands for molality, and this is moles of solute per mass of solvent. Now, in this case, the mass of solvent is in kilograms. Over here, the mass of solute is in grams. So just so that you have an idea of units as we're going through this. So this is moles per kilogram. So if we substitute this in, if we take the little m and we plug in moles of solute over mass of solvent, we get IKF, moles of solute, which was on top, divided by the mass of the solvent, which was on the bottom. So we can reorganize this to get this in terms of the moles of the solute. So the reason why we're doing that is because over in this equation we have moles of solute. So if we do that, we get delta T, the freezing point depression temperature change, times the mass of the solvent divided by IKF. That's just if we reorganize this to have moles of solute on the left. And then what we can do is we can take this and we can plug it in over here. So what I did in this step was I just took this equation as it was and I substituted it in on the bottom. And now I'm just going to reorganize this to make it look a little clean. So now what I'm going to do is I'm going to take these two factors, which are on the bottom of the bottom, basically. So this is 1 over 1 over. I'm going to bring those up to the top. And we get a nice clean equation, which is I times the freezing point depression constant times the mass of solute in grams divided by delta TF and the mass of the solvent. And this has to be in kilograms, and that comes all the way back from the molality. So now you have one clean equation that you're going to use for this experiment that links all of the factors together and how we're going to get the molecular weight. So now let's look at what a cooling curve is. So a cooling curve is where we take, in this case, this is a pure liquid, like our acetic acid, and we start to cool it down. So you'll notice as time goes on, the temperature goes down, and that's because we're cooling it. So this could be putting it in an ice bath, or it could be putting it in a refrigerator, for example. So what we'll notice is that we get this interesting shape. We get this little dip that goes down, this little well, and then after it goes down, it comes up, and then it stays flat, and then eventually it starts to go back down again. So what's happening here? So what we're doing is we're cooling it down over time, and then eventually we get to the freezing point. So this line right here is the freezing point for this solid. So if this were water, it would be 0 degrees Celsius. So now what's interesting is you see we go below that temperature, and yet we're still a liquid. This is called supercooling. So this dip where we are still liquid, but we're below the freezing temperature, is called supercooling. And what this is it takes some time for, as you cool the liquid down, it takes some time for the solid to start to form. What you need really is you need a nucleus, something for the solid to nucleate on and actually grow its crystal structure off of. It's like think of it as like a template where you can start to then put the Legos in to make your solid crystalline material. So what happens is there's a kinetic effect. You're cooling it down, and you're cooling it down, in this case, much quicker than it can actually form a solid. So eventually it gets to the bottom, and then right when it gets to the bottom, this is the moment where it starts to crystallize, and then it jumps back up to the freezing point. So now what we have is, as it jumps back up, we have a solid and a liquid together in equilibrium. And as time is going on, we're still cooling it, so we're still taking heat out and taking energy out, but the temperature remains flat. So if you remember back to chapter 11 in ebbing, what this is this is the phase transition. So as time is going on, more and more solid is getting produced here until we get to the very end of this linear part, this flat linear part, and then we start to cool down again. So when we start to cool down again, this is when we've created our solid. So we go from here, we're going from approximately, let's say 10% solid. As we continue along this line, we're cooling it, making more and more solid, and then eventually we get to 100% solid. Then we can start to cool that solid down and the temperature of the solid falls. So this is what a cooling curve for the pure substance looks like. Now let's compare this to the cooling curve for a solution. So we still get supercooling. That's here. And you'll notice here there's a key difference. If you compare the freezing point for the pure solid to the freezing point of the solution, you'll notice that the freezing point is lower. And this makes sense because freezing point depression says our freezing point should be lower. So the fact that we have a lower freezing point in the solution is consistent with freezing point depression. So we get our supercooling, and now what's interesting in this case is we don't get a flat line, but we get a line with a little bit of a slope. So here the line is flat, here the line is sloped. And the reason for this is because you have to think about what's going on inside of this solution as time goes on. So we're still going from about 10% solid here to 100% solid here. But what's happening is as time is going on, we are creating our solid, and the solid doesn't have any of the solute in it. The solid is just the pure solvent. So this would be the water, and as the water is freezing out, the solution that's left behind is becoming ever more concentrated with that salt that's left behind. So the concentration is increasing, and as the concentration increases, the freezing point is going to go down, right? With freezing point depression, the more concentrated the solution becomes, the lower the freezing point will be. And that's what we're seeing. As we freeze out the ice, the solution that's left over gets more and more concentrated, and then that's why we get a sloped freezing point. Now, eventually, we're going to freeze out all of the water. That's going to exclude all the salt. So we'll have salt and we'll have frozen water. And then again, after that, at that point, we start to just cool the solid. So now let's look at how we're going to do this experiment. So normally, if you were in lab, the first step would be to identify the freezing point of the pure solvent. So we need two numbers in this experiment. We need the freezing point of the pure solvent, and then we need the freezing point of the solution. That's going to allow us to get delta T. So we need to get those two numbers to get the delta T. So what you would do is you'd walk up to the hood, and in the hood would be a burette. And in that burette would be pure acetic acid, 100% acetic acid. We call it glacial acetic acid. So what you would do is you'd walk up to that burette and you'd take an initial reading. And in your case, your initial reading was 1.27 mils. We read off 2 sig figs on the burette. So then what you would do is you'd start to open the burette valve and allow the acetic acid to flow into a clean, dry test tube. And we're aiming to get about 10 mils. So you see we're getting close, and you stop at around 10.29 mils. So we've added, in this case, the difference between these two numbers in volume. So by taking the final burette reading minus the initial burette reading, we can get a volume. Now, what we need is we need to know what the mass of the solvent is, because in terms of molality, we need to know how many kilograms of solvent we had. So what's going to help you go from volume, which we have measured, to mass is the density. So we give you the density here, which will allow you to go from milliliters to grams. So you have to use this as a unit conversion. So now you have your acetic acid sitting in your clean, dry test tube. What the next thing you're going to do is you're going to prepare an ice bath. We're going to use this to cool down the solution in a beaker. And then you're going to place your test tube in the ice bath and use the vernier temperature probe to stir the solution. So now we're going to start to record temperature as a function of time. So let's look at a little video that shows this. So on the right here, what I have is I have the cooling curve graph that we actually are going to measure on the vernier. So there's a computer screen here, but I'm going to show you what was on the computer screen. And then over here we have one of our lab technicians who kindly stayed behind to create this video for us. So she has her 10 mils of the acetic acid in her test tube. She has the vernier probe here, and she has her ice bath here. So what she's going to do is she's going to start the experiment on the vernier. So now, as she puts the temperature probe in, this thing is going to start to collect data. So we're going to collect a whole bunch of points here while it's flat, just to get an initial temperature. Now she's going to put it into the solution, and the temperature is going to start to go down. Now, if you look very carefully, what's going to happen is, as we're cooling down, if you look very carefully, there's going to be a moment where we start to see solid. So watch this area very carefully, and then you'll see it. So here we're continuing down our curve here as we're cooling, and it may take a few seconds. Okay, so you saw the instant that it turned solid. At that instant, we get to the bottom of this well, and then as the minute that solid forms, it jumps back up. And now what she's doing is she's keeping it in that solution and allowing it to equilibrate. So now we're seeing that the freezing point of that pure liquid. So we started with a room temperature sample. We cooled it down. The moment we reached the bottom of this, it turned white. You saw that. And then it snaps up quickly and goes flat, and we get our temperature. So now the second part of this experiment is where we identify the freezing point of a solution. So to prepare the solution, what you do is you take your solvent that you just cooled down, it's a solid, and you put it in some warm water to melt the acetic acid. So this gets us back to liquid acetic acid. And then you go in and you weigh out 1.0488 grams of the unknown. So the unknown is a solid. It's a non-ionizing solid, so the I is going to be 1. And then you add this to your test tube containing the acetic acid. So now from this, we have the mass of the solute that we're putting in. And then you stir until it fully dissolves. And then you're going to repeat the cooling curve procedure and collect the second cooling curve for the solution. So we're going to, again, we're going to have our ice bath. We're going to cool it down. We're going to measure the temperature as a function of time, and we're going to get two curves. So now, on vernier, this is what it would have looked like. So the blue trace was the first one that we looked at. The orangey red trace is the second one. So if you look at the orangey red trace, again, we see cooling, and we see much bigger supercooling. So if this is the freezing point temperature, we're going much lower relative to the pure solution. In this case, we're only going about a degree, maybe a degree, 1.2 degrees below the freezing point. Here, we're going as much as almost 10 degrees below the freezing point to get it to freeze. So again, here we're waiting, and then all of a sudden it turns into a solid and it snaps back up. So why do we see this extended supercooling in the solution? Well, if you remember what I was saying, this supercooling region is the time it takes for the solid to start to form. Now, in pure solvent, that's pretty easy because we don't have anything in there to disrupt the formation of the solid. In a solution, not only do we have the solvent molecules, but we also have the solute molecules sort of homogeneously mixed together. So when this thing nucleates and wants to start to form the solid, it has these solute molecules that are there hindering it from really lining up and locking into forming a solid. So that's why we get an extended supercooling here. We have to cool it down much more in order to get it to turn solid, and then we get our solution freezing point. So you'll notice, as we expect with freezing point depression, the temperature is lower, and it turns out that this student didn't keep the experiment going for very long. They just did it for a short period of time. Had they kept it going, what they would have noticed was this thing start to tail down, which is what we saw in the earlier slides as it starts to freeze out the solid. But this student didn't do that. And actually, this is going to work out much easier for us to analyze, because what we're going to do is we're just going to take the average of these data points. So we're going to take the average of these data points to get the temperature and the average of these data points to get the temperature. And then that's how we're going to get the two temperatures for the delta T. This is the data sheet. So you'll see that we have the final burette reading and the initial burette reading already put in. This was the data that we collected. So we started at 1.27 mils and we ended at 10.29 mils. And then we also have the mass of the unknown compound in grams. That was what you measured out in part 2 on the balance. So what your job is to come up with the volume of the acetic acid by taking the difference between the final and the initial burette readings. The mass of the glacial acetic acid, I gave you the density, so that's there. It's also in the lab book. So you can use the density to calculate the mass. And then finally, we need to convert this into kilograms. And the reason for that is because molality requires the solvent to be in kilograms. Now, the only other two measurements that we have to get are the freezing point of the glacial acetic acid and the freezing point of the solution. So another thing that you're going to get on Blackboard is the data itself. So if you look at the data sheet, this is going to be the Excel spreadsheet that you get. There's going to be a data trace for the pure solvent and data trace for the solution. And what I want you guys to do is, normally we would do this a little differently. We would fit these to a line and then see where it intersected back over here and then get that data point. Since you don't have the Vernier software at home, we're going to do this a little differently. And it's a little bit easier, but it's going to give you perfectly fine data anyway. So what we're going to do is we're just going to take an average of the data points after they have stabilized, both for the pure solvent and for the solution. Now, this is going to be slightly less accurate for the solution because there is some cooling that's going on as the solution becomes more concentrated, but we're just going to assume that it's okay. And it is. It'll give you perfectly fine numbers. So what you'll do is you'll go and you'll look and see, okay, at what time did this thing stabilize? Well, this thing stabilized at around 60 seconds, and then it stays stable until around 80 seconds. So what you can do is you can run down in your data, And at 60 seconds, you can take an average. So you can use the average function in Excel to average all of those data points and get an average number. The reason why we're averaging is so that these little slight fluctuations in the numbers, we sort of take that out and we just get one data point that's robust from all of those data points. And then you're going to do the same thing. You're going to take the average of the data for the solution, which starts at about 150 seconds or so. So you'll see, if you look at the data trace for that, at around 150 seconds, it stabilizes at about 12.6 or so in here. So if you start from about 150 seconds all the way to the end, taking an average, that will get you those two data points. So those data points you'll enter in here, one for the pure solvent, one for the solution. And then you can take the difference between the two. The delta T should be a positive number to work with the equation that I gave you. And then from all of this data, you can get the molar mass. Now, there is a second part of this experiment. It's called Part B. We are not going to do Part B. I know in your book it has a sheet for it. The reason why we're not going to do Part B is because it's a little too complicated to explain in this format where we're digitizing the labs. And also, in all honesty, it's a little less important to the whole lab structure. So we're not going to do Part B, and Part B would just be looking at different crystals coming out of solution from a mixture of sodium chloride and potassium nitrate. But we're not going to do that part of the experiment because it's a little too difficult to explain this way. So this should be everything you need in order to complete Experiment 13. At the end of Experiment 13, you're going to fill out this data sheet and upload it to Blackboard for your instructor to grade. Okay, so then the next one, the next video will be coming out soon, and that will be for Experiment 18.